Hey everybody, this is Garrett with Earth and Time, and today we're coming to you from Monrovia Canyon or Monrovia Wilderness Park in Monrovia, California, about 10 miles or so east of Pasadena, California, on the north part of the greater Los Angeles region. And the reason I'm here is I'm actually visiting these amazing mountains. So these are really unique mountains here in Southern California. In fact, they're unique mountains in most parts of the world, and they're so unique that they're actually rising at a faster rate here than even the Himalayas, things like Mount Everest. So come join me today. Let's learn about this fascinating place, what are known as the Transverse Ranges here in Southern California, and learn about the geology of these amazing mountains. Let's get to it. If we look down in the valley, so I've come up this hill here, so that is the town of Monrovia and Diorite and a couple other towns that are down that direction. And we're actually looking down this canyon. Now, what's interesting about this canyon and the geology here is, if you can see behind me, these canyons or walls are very, very steep. And what's interesting about that is it plays a particular role in certain things that happen here in Southern California, specifically the flooding that occurs here. So visiting these mountains, we can talk about several natural disasters, actually. We can talk about earthquakes, we can talk about landslides, and we can talk about flooding. So we can really see how steep these cliffs are as I look up here, and you'll see a number of rocks outcropping here, and these are all diorites. So diorites are a type of intrusive igneous rock. And what's interesting about these, this, if you will, speckled appearance. So what we have here is a lot of quartz, some feldspars in here, as well as a lot of things like biotite and amphiboles or hornblende. And it makes a salt and pepper looking rock. And this is called a diorite. So different than granite that usually has more pinks and it's a little bit more white, it's kind of pink, white, and black. Diorite actually is more this kind of salt and pepper look to it. So if you ever see these salt and pepper rocks, then you know they're a diorite. So these cliffs are made up of this fairly resistant diorite, which we can see in the cliff face up there as well. Now, these diorites that are here are Cretaceous, which means they're from the later part of the dinosaurs. So during this time, there were island arcs ramming into the western part of the western United States along a plate boundary, and they were creating volcanoes and large batholiths. The batholith most people are most familiar with during the time of the dinosaurs. It's actually more Jurassic in age, but does continue in the Cretaceous, is the Sierra Nevada batholith. This would be part of that same series, just a little bit later in age, being that it's Cretaceous as opposed to Jurassic. Now, there is a wash down here. There is actually pretty active running water, and I mentioned that we can talk about different natural disasters. When we think about rainfall in California, which actually doesn't happen very often, but I'm actually here for New Year's 2026. Happened over the last couple of days was we got a lot of rain here in Southern California, and an unusual amount of rain. And the issue the mountains have here is, one, they're very steep. So any rain that falls on them quickly goes to the lowest point, which are these canyons. And the issue with flooding is a bit exacerbated because of all the fires that have occurred here in Southern California as well. So you don't have any trees or soil that help soak up some of that moisture as it comes down. The steep hillsides that are here, along with the lack of vegetation and a lot of topsoil, it means all the water has to go somewhere. So it all gets channeled down into these canyons pretty rapidly. What could be just a minor amount of rain quickly coalesces into a raging torrent. And if we listen for just a minute, we can hear that water raging down this canyon. The next question to ask then is, why is there even a canyon here in the first place? Well, it turns out that since the time of the Cretaceous, these rocks have been through a lot. They've been tortured, if you will, through a series of tectonic events. Most famous, of course, and the latest really, is the San Andreas Fault zone that established, about 6 million years ago into this area. And these mountains really started popping up maybe in the last 1 to 2 million years. So they're fairly young, but what that means is they're under a lot of stress. So there's a lot of deformation going on. And what will happen is you'll have zones of weakness in these rocks, like along this canyon. where through time, water will preferentially want to travel down and eventually carve out this greater canyon area, which gives a focal place for, again, when we have these big rainstorms, for water to come out. Now, California's done a really smart thing, and they have these catchment basins at the bottom to catch the debris as well as the water, and made reservoirs out of them. So I was talking about the faulting and the San Andreas Fault. So these mountains that I'm in are actually pretty unique here in Southern California. They actually run east to west. Most mountains, when we think of them in the western United States, the Basin Range, the Wasatch, the Sierra Nevada mountains, generally run north to south-ish. These actually go east-west, and that's because there's actually a bend in the San Andreas Fault. And so these mountains are rising rapidly and in a very different direction than the other mountains, and are trending in a very different direction than the other mountains that we see here in California. And with the compression that's taking place, or the thrust faults, you start seeing some really unique features within these rocks. And this is a nice example of that. So you'll see there's a shear fabric almost going up and down, and the trees are taking advantage of this. So these trees are telling us a lot of times where we see faults or fractures, because water gets into those sections and the trees can grow and get water out of them. And so this is likely a fault zone, or at least some kind of major fracture zone. And I can see the difference in the colors of rocks here telling me there's something different happening on that face compared to what I see as I drift down to the right or to the left. And we can see another tree taking advantage of another fractured zone in here. There are a series of thrust faults that come through this section, and I'm actually wondering if this isn't either a splay of one of those or actually one of the thrust faults itself. One thing I'll say is most of the rocks here are pretty homogeneous. They're all this diorite. Now, I did see there's a couple different ages of diorite here, mostly around the Cretaceous, and there's a couple different formations of diorite here, different times of intrusive igneous activity. And we can even see there's been some later events, like this little dike coming through here, quartz dike cutting through at a later date. One thing to consider is we talk a lot about the San Andreas Fault and strike slip fault systems and how dangerous they are, and how seismically active the fault system here is. What's interesting about these mountains is these are also very seismically active, and because they're in a thrust type of geometry, they have the potential to be much more devastating than a regular strike slip fault. So the Sierra Madre Fault that runs just south and west of us here is a major fault that you really have to consider. If that moves, it's going to be a major tectonic event or major earthquake event here in Southern California. Here's a look at some of the fractured diorites here along the creek, and I can stand here and we can get an idea about how much water is coming through this creek right now. I can see there's reeds that are bent over down there, so it looks like they got quite a bit of water, but not nearly as much as I thought I'd see with all the rain we've had here in Southern California over the last few days. While I'm looking at these mountains behind us, let's talk a little bit about the rate at which these mountains are starting to rise. Now, I mentioned at the opening of this video that the mountains here are rising faster than the Himalayas. These mountains are rising right around 10 millimeters per year. The Himalayas are rising about 5 millimeters a year. So there's portions of these mountains that are rising twice as fast as, say, something like Mount Everest. So then, of course, the question becomes, well, why isn't there, the Himalaya type mountains that are here? And the answer to that is the faulting here is fairly young. So the faults here and these mountains popping up really started moving around 1 million to 2 million years ago. I've seen estimates less than 1 million as well in some publications. So these are really young mountains, all things considered, whereas the Himalayas have been moving since about 40 to 50 million years ago. The other thing is that these types of rocks, although diorites make pretty good cliff formers, they do erode, especially when they get fractured, very easily. Whereas some of the rocks that are up in the higher parts of the Himalayas, there's also a lot of metamorphic rocks there. So they've had both more time and they have more resistant rocks than really what we're seeing here within the San Gabriel Mountains, or at least this portion of the San Gabriel Mountains. So that is why this transverse range, as they like to call it, this east-west mountain range, the San Gabriel Mountains, aren't as tall as something like the Himalayas, but they are rising much, much faster. They're just also getting eroded. And that erosion's happening two ways. We talked about the water coming through here. So when you have rain, you start moving debris, it goes down these canyons. You also have just slope failures as well. Another major issue here in Southern California are landslides. Now, those can be caused by water, because water creates lubrication, which allows those rocks and landslides to occur, but they could just happen because of instability and gravity through time. And as we look at the face here to the south, we can actually see where there's some basically bare rock or brown spots, and those are areas where there's probably a landslide or a slope failure, and we can see a series of those going down here. And this gets at this idea that when you have a really steep angle here, something over 30 degrees, it's past what we geologists call an angle of repose, and that's when these cliff faces start failing just due to gravity. And then of course, if you add water, it just makes it that much easier to fail. And if we take a look at how steep these mountains are, you get a real idea about how with just some water and gravity and time, these hills can just start crumbling. In fact, this may be a little slump scar here where part of this face broke down and slid down into the creek. In fact, you see another one here, so we can see a little landslide, if you will, a small version of one. I can't pass up looking close at one of these rocks. So this is another diorite, has that salt and pepper look, but it also has a series of what we call dikes going through it, which is pretty cool to see. And these are pretty quartz rich. In fact, you can see they're actually tougher and more resistant, if you will, than the surrounding rock. And you'll see it actually is raised here. So this is all eroding much faster than these pieces. And again, going back to the idea of why we don't have Himalaya-sized mountains here, right? It's both, haven't had enough time to get them that big, but also that these rocks are more easily erodible. And this is actually a nice look at a debris flow or pile that came down this river sometimes maybe hundreds of years ago or thousands of years ago. You'll see there's a tree on top of it, but all this is eroded down. And these are all large boulders that have come from the tops of these mountains up here, have been traveled down through gravity and through water. Another example of the erosion and landslides and some of the natural disasters you have to think about here, as well as this concept of these mountains are actually eroding fairly quickly. Geologically speaking, if you ever make it to this part of Southern California, which I highly recommend, I've absolutely fallen in love with this area, Monrovia, California. It's right along old Route 66. The town was set up in the 1880s. Cute downtown, beautiful scenery, amazing geology. And this is the Monrovia Wilderness Park that I'm hiking around and walking around. And this is a nice example of a dike going through some of these diorites, and you can just see the distinct difference. So what does this tell me story-wise? Well, it tells me that you had the original pluton in place here, which would be our diorite, and then there was some later event that moved hot fluids through fractures or created fractures within the diorite, and these were deposited much later. It's a concept in geology we call cross-cutting relationships. I will say the scenery here is a bit magical. Look at how these trees are exploiting the fractures in the rocks to grow and to get water. And I just see this time and time again through here. So the plus for here is that these trees actually create some kind of stability in these rock faces. The downside is these rock faces aren't very stable for really long periods of time. And look at that one. This tree went all the way out. It's tagging into this fault zone right here, a fracture zone that runs right through this section. Pretty amazing. Talking about debris and debris flows, here's a tiny little debris flow. And what's fascinating about this one is I can come up here, and this is actually a little fault zone. And how I know that is I can see striae or striations in a surface here where these rocks have moved past one another. Pretty cool to see, and an example of the type of faulting here. In fact, here's some more here, so we can see where the rock has actually been polished And these are striae or striations, and we measure these as geologists to get an idea how these rocks are moving. In this case, they're moving up and down, and knowing that we're in a contractional compressional system, there's a chance that these could have been moving up. Pretty cool to see what we call slicken lines. Picked up this rock, and we can actually see the slicken lines just below my thumb on this rock that just fell down from this face. One thing is, I love all the rocks here, but it is absolutely beautiful and green in this canyon. I've enjoyed just the hike up, not just to see the rocks, but just to enjoy all the life. Thank you everybody for joining me today to check out the Monrovia Wilderness Park, the Transverse Mountains here, the San Gabriel Mountains, talk about how come they're forming, the idea that they're growing at twice the rate, if you can believe that, is the Himalayas. It's pretty crazy. How the San Andreas Fault plays into that role, and learning a little bit about how come there's so much flooding here and why floods are so disastrous, and some of the other natural hazards here like landslides. If you enjoyed this video, please give it a thumbs up. Leave a comment down below. Have you all ever been to Monrovia Wilderness Park before, or another area here along the San Gabriel Mountains? If you haven't as well, please subscribe to this channel if you enjoy learning about science and history here. This is a big year. This is the 250th anniversary of the United States, so I plan on hitting some of the major parks and talk about the geology there, as well as some of the major historic sites within the country. So come join me to learn about all those places and learn about the science behind a number of them. So with that being said, thank you all for joining me today. Happy New Year. I hope you all have a great one. See you on the next adventure. Bye for now.